let's begin. Whoopsies. Let's begin. All right. Good afternoon, everybody. My name is Ethan Hoban. I'm the president of the Electrical and Computer Engineering Honor Society here on campus. That's called Eta Kappa Nu, some call it HKN. We are IEEE's official engineering honor society. And we basically, if you are in the electrical or computer engineering department, if you are at a sufficiently high student rank within your major and within your year, that being junior or senior, you get an invite from me. If some of you are that way, you may have got an invite from me like on Monday because I procrastinate. So if so, I hope to see you tomorrow for the initiation. Otherwise, today I'll be presenting stealth design principles. We did that already? All right. So who am I? So I graduated UAH's electrical engineering program in May 2023, and I'm currently working part-time on my electrical engineering master's degree here. This is not updated, I gotta fix that. I was a full-time software engineer at Northrop Grumman on the GWS program, but I am now a Tempest engineer on the Sentinel program. Anyone who wants to know about that, we can talk about it later, really cool stuff. I'm a habitual project collector. You can see some of these. I made that specifically to look illegal, and it's very entertaining, honestly. The problem with that video is I flipped the detonator, and then it sat there for 30 seconds doing nothing, and then set off car alarms when it exploded. But also, as you can see, rocket enthusiast, that's me flexing, you know. All right, what to expect. So, I've done several talks related to stealth, low observable technology, electronic warfare techniques prior. Show of hands, who was here for the stealth presentation last semester, or who saw it? You, I believe you did, and I think you were there too. So that was a good presentation, and it gave more of a deep dive introduction into stealth, things like radar cross-section, radar performance materials, target shaping, that kind of stuff. And while we will briefly mention it and discuss it here, we're not going to go to the same level of deep dive. If you are interested in catching up, I have links to the slides I can provide, and additionally, all of these lectures are uploaded to YouTube. There's a YouTube channel we have. You can watch them at your own leisure as many times as you need and at whatever speed you need. So we'll do a brief introduction, so I'm not going to dive too deep into that. Then I'll do another brief introduction and discussion of what radar cross-section is. That's an extremely important topic, and whenever we're talking stealth, we're really just talking about minimizing a radar cross-section and or minimizing radar returns. But again, that's just a function of your radar cross-section. We're going to cheat and do what they did back in the 60s and 70s and use optical approximations here. It's a really good way to build an intuitive understanding of stealth and low observable technology. It is not correct. It's close, but it's not enough. In real life, you have to pay a lot of money for what's called FICO software, which is a type of high-frequency analysis software. Very expensive, but it gets the job done, and it's what allows us to do the crazy stuff that we do nowadays with low observable and stealth technology. And we'll kind of discuss what that is later on. We'll discuss the fundamentals, but there's only really one we care about all that much. And then we're going to go through an example of how to stealth a plane. My goal by the end of this talk is that I could show you a plane side by side with really almost anything else, and you could tell me which has the lower radar cross-section. And this helps, because at the end of the day, no single person can really sit down and design an entire stealth vehicle. That takes teams and teams of people. But you can look at a picture of a new Chinese plane and see, is this a stealth fighter or is this garbage? Most people apparently can't do that, including you. Which is fine. I am legally blind. Okay, all right. And then at the end, we're going to do a let's design a stealth vehicle. So, introduction to stealth. After I'm done talking on this slide, whoever can name all of these planes, they get a cookie. So, stealth, which, huh? You won't name that one.
I have two of them here. It's an F-22 Raptor right there, and there's an F-35 Lightning II.
Good, so far, so good.
They're Lockheed Martins, both of them are Lockheed Martins.
So, stealth, also known as low observable technology. Whenever you're looking at job requisitions, this is a good keyword to remember. If you see LO engineer, that is a stealth engineer, and it is a job you can get at the entry level. So if you can get lucky, I recommend it. So look up for LO engineer, a company called Anduril's hiring a whole bunch of them in Costa Mesa, California right now. But is basically, you use advanced materials, analyses, and other things like ECM techniques to minimize the various signatures of a system. Stealth and low observable, like broadly, is not just radar, but radar is by far the most important component. There's things like infrared, acoustic. That is becoming more important. Laser cross sections, EOIR optic systems are becoming more prevalent and becoming more advanced and almost in some cases preferred, but radar is still the most common thing you're gonna run into, so it's best to design around radar. And then, of course, as I said, stealth is predominantly used to combat radar, which enables aircraft to operate freely and with greater liberty. Modern missile systems and modern anti-aircraft systems can comically easily handle almost any aircraft. There is no dodging these things. It's extremely hard to trick them. Nowadays, you have to avoid them entirely to have a decent shot. Otherwise, you're running the risk of getting shot down. So, I'll give anyone a chance to name all 6 of these real quick. Minus Kevin, he's not allowed.
Yeah.
What do you got?
F-117, F-22, B-2, F-35. It's the RQ-47,
Close, X-47B. It's a Navy demonstrator.
YF-118,
This is not the YF-22.
X-118.
It's called the Valkyrie or something. It's a Boeing stealth demonstrator.
Called the bird of prey.
Yeah, that one.
Bird of prey.
Yeah. For anybody who saw the F-47 release that they came out with recently for Boeing's award, it looks starkly similar to this.
And if you saw the Air Force new recruiting video, they have a better, very short shot of
Yeah.
what it is.
They have a half-second clip.
Or if you would recognize the F-22 over here, if you've seen any Transformers movies, you will see that is Starscream right there.
Starscream. Who knew Starscream was a Lockheed Martin ad?
F-22 Raptor.
All right, real quick disclaimer. I work at Northrop Grumman. Northrop Grumman has made a lot of these vehicles, particularly has made this, and has contributed to all the others, minus the Boeing one. But I personally have not. And I promise I'm not leaking any classified or confidential information. All of this information is open source. All of my information comes predominantly from this stack of textbooks, and I'll discuss these more later on. So I promise we're not doing any code blues here. So we're going to go into radar cross-section. I assure you this is the only math formulas in the entire slide. I kept it light this time. So radar cross-section is a value that expresses the magnitude of a radar return relative to the apparent size of that target in square meters. Basically, how much energy is reflected per square meter. And the actual official unit for radar cross-section is dB decibels SM, dBs per square meter. You'll see a lot of stuff if you Google radar cross-section, people will express it in units of just square meters, but that's not actually very helpful at all. And in real life, you have to normalize by adding that decibel scaling to it. It's like 20 log 10 of however your square meter size is, or your radar cross-section. And obviously, the larger your radar cross-section is, the easier you are to detect. And the actual official mathematical definition is actually rather horrific, and these are just still shortened versions of it. But as a concept, it's the power reflected back to me, the receiver. So I'm a radar, I send a signal out, it bounces back. The power reflected back to me per unit solid angle, that's where it starts getting terrible. But I'll explain what this means, because this is important to understand. Divided by the incident power density divided by 4. Incident power density is how much energy actually hit the surface of your target and ended up reflecting back to you. And then there's all that math, but we don't really need to care about that. If you were to Google the radar cross-section of something, like an F-22, it'll tell you it's like 0.0001 square meters. But the actual truth of the matter is you don't get that lucky. Unfortunately, if we just think about shadows, which is what I say here, I try to explain this in case of shadows. If you're holding a flashlight and you have a model sitting somewhere and you flash a flashlight at it, it's going to cast a shadow. What happens to the shadow of a complex shape as you move around it and illuminate it from different angles? The shadow changes shape. And that's exactly what happens with the whole unit solid angle. It's also known as viewing aspect or viewing angle. If I'm looking at you head on and I'm a cone, right? I look like a circle. So the radar is going to see, it's actually going to be terrible because it's going to reflect away, but let's say it's a circle or cylinder. You look straight on, I'm a circle. What happens if you look this way? I'm a rectangle now. That's basically the whole concept of unit solid angle, viewing aspect, all that kind of stuff. It's basically, here's my radar, I project out a field, an area, like a square area that I can see, and then energy comes back to me. That changes completely depending on where you are relative to a vehicle. So in real life, that's why radar cross-section is extremely difficult to calculate, measure, analyze, because it's actually extremely complicated. And we like to just simplify things out and just say it's a flat number, maybe it's an average, maybe it's a best case, worst case scenario, that kind of stuff. But it's important to know that that's what we're dealing with here. And from a stealth design perspective, we try to minimize that. So, everyone's familiar with how mirrors work, right? We have reflection, absorption, scattering, but we're gonna ignore that one for a little bit, and transmission, right? Mirror, glass, you're gonna have some energy reflected, some energy absorbed, some energy goes through. Most of the time, until you start getting really complicated, you can approximate how electromagnetic waves interact with materials and surfaces as if it was a piece of glass and the electromagnetic wave was light. Funny enough, light is an electromagnetic wave. So it does actually observe and follow a lot of rules, and lower frequency energy also does observe and follow a lot of the same rules. Minus diffraction. It starts getting weird at diffraction, and that's why stealth gets hard, but we're not going to have to deal with that much today. So, obviously, the optimal solution for a stealth vehicle is to just be fully transparent to radar, and it just passes right through you, it never interacts, perfect. Obviously, that's fantasy. For the most part, we can do it sometimes in certain places, but not for an entire plane. Particularly because a human is in that plane, and humans have a radar cross-section. What's the radar cross-section of an average human? Take a guess.
About 1 square meter.
It is about 1 square meter. Ish. It's good. But, okay, obviously your radar is not gonna just go through you. That's not gonna work. Next option is to absorb all the energy into yourself so it doesn't reflect or go anywhere else, you keep it. And that is actually how we currently try to attack that problem for the most part. We have radar absorbent materials that are capable of absorbing over 99% of inbound energy. Now, of course, that comes with the problem of now you heat up. So you traded one signature, that being your radar signature, for your infrared signature because now you're warmer. But it's still a good trade. So we coat almost everything in radar absorbent material, but it's still not enough. Advanced radars are blasting out so much energy and are so sensitive that even if you absorbed like 99.9999999% of energy, still, if you are just relying on absorbent material, you will give them a return and they will see you and be able to track you, which is not good.
So maybe I'm crazy along this line of thinking, but if you're absorbing all that energy, and I don't know how much the absorption is, but that seems like a really good way to result in issues with overheating the plane.
Yeah. You trade your radar signature for your infrared signature, you'll get very warm. And actually, a paper just came out earlier this week regarding novel high temperature radar absorbent materials. Because not only is radar absorbent material, as you said, as you get better and better, vulnerable to overheating, these materials are polymers that break down pretty easily. Current RAM is what's restricting our flight speeds. The top speed of our vehicles is restricted by how well our coatings hold up under that aerothermal heating.
Okay.
So the answer is, it's a huge problem, and the people who are working on it are about to make a whole lot of money because they came up with a new type of ceramic, flexible ceramic RAM coating.
I'm curious, what's stopping someone, a malicious actor, from using radios, at like an excess of radios to intentionally overheat systems?
Nothing. That's basically a laser weapon. We do that. But it does take a lot of energy.
Okay.
It does take a lot. Yep.
Doesn't this mean that we can tell when we're being tracked as well, based on how hot the vehicle gets?
Potentially. That is a good way. But also, nowadays, we have very advanced sensor arrays that will also pick up on that same energy. But yes, you could. It'd be an interesting way to do an extremely passive system if you were worried about like unshielded local oscillators or something. That whole unshielded local oscillator thing, if anyone's familiar with the whole radar detector rules, you can actually, there are radar detector detectors. So you would think if you're just passively listening, they can't hear you, they can hear you. So do not think you're safe with a radar detector in Virginia. You'll get pulled over and fined. Okay. Yes, and the last one The next factor to consider for our solution is to shape the vehicle, as in position the mirror in such a way that energy that hits us does not reflect back, reflects somewhere else where ideally there is not a radar receiver. That's not always the case, but ideally there is not. So now we're going to take those three concepts and we're going to try and stealth a plane. Our options are transmission, absorption, and reflection. So for the rest of this slide deck, we're going to discuss how to take this stuff into consideration to change how we design planes and basically prevent us from getting shot down. And we're going to start by looking at everyone's favorite commercial airliner, the Boeing 737. So, first thing, I'm a radar, you guys are all radars, you're looking right at this plane. What are the first problems you might see looking directly into this thing's face? Well, anyone, any ideas? What do we got?
Big cross section.
Pretty fat,
Pretty big.
pretty big. And well, I'll tell you, and we're gonna get into this, I've got like 4 slides on it.
Very colorful as well.
Yeah, it's very colorful. But, huge issue,
Turbines.
these engines. Huge problem. Engines, large trailing wings, large vertical and horizontal aft fins, ailerons. But, and we'll get in as to why these things are issues, but keep in mind, when you're looking at a vehicle, you're looking for engines, wings, wing sweep, total like face-on cross-section, and you're specifically, this is a big one, looking for any 90-degree angles. And we'll get into why that's a huge issue in a second. But the answer is you all already know this. You've been familiar with it since you were probably about 4 years old. And we'll get into that in a second. So, we're gonna break this out. The average jet airliner has a radar cross-section of about 1,000 square meters. That is massive. From a radar's perspective, it lights up like a Christmas tree and is extremely easy to discern what's going on there. So, for example, if you ever see reports of a commercial airliner being shot down in war, it was 100% on purpose because they know exactly what that thing is. There is no hiding what this is. It is obviously a commercial airliner. It is not military. No military vehicle worth its salt has a square meter, has a cross-section of 1,000 square meters. But it has a litany of issues, as mentioned. Long wings, highly reflective. It's almost entirely made of aluminum or aluminum alloys. The wings are not swept far enough. And we'll talk about wing sweep. From an aeronautics perspective, for any aerospace or mechanical engineers, you're probably familiar that wing sweep helps you with Mach angle, helps you with high-speed flight, all that kind of stuff. Funny enough, wing sweep also is extremely important for stealth reasons, and we'll get into that. Engines are entirely exposed and directly front-facing. If you think about what an engine is, it's basically thousands of bits of metal just spinning at comically high frequencies and just projecting all that energy out. Think of it as a bunch of little mirrors just spewing energy everywhere. Then, obviously the vehicle has no ram coating. So it's not absorbing anything, it's reflecting almost everything back. The vehicle is made entirely of aluminum alloys, highly reflective, vertical tail surface and horizontal tail surface. So, let's talk shop. How is it that the Flying Dorito, otherwise known as the B-2 Spirit, which has a wingspan larger, almost double that of a 737, have a radar cross-section 1,000,000 times smaller? How did this happen, right? This vehicle is bigger, it's heavier, it's slower. I think it's actually a bit faster than this thing, and yet this thing glows up like a Christmas tree. This thing is the size of a bumblebee on radar. How'd they pull this off? The answer is with a lot of money, but a lot of science too. So, we're gonna drop some stuff to look for. When you're designing or thinking about stealth vehicles, things you need to care about. Corner reflectors, tapered conductivity, and we'll explain what all these things are, serpentine inlets, and management of traveling surface waves. And how this is done, we'll begin. As I said, you've all been familiar with these since you're 4 years old. Corner reflectors, also known as retroreflectors, are used everywhere. Bikes, the funny vests that the people wear at night when they're trying not to get hit by a car. They're a great way to keep you from getting hit by a car, but it's also a great way of helping you get hit by missiles. So it's not great. The whole point of a corner reflector or a retroreflector is any 90-degree angle, if hit by any angle of ray, will reflect that ray back to where it came from. So if you aim your flashlight at this retroreflector and you move all over the place, it will still look bright to you because the light will come right back to the source every single time. Which means if you have one of these on a plane, that radar is going to hit you and go right back. And they're going to see you. And they're going to see you pretty well. So you need to avoid these. But let me go back real quick to this. This is the largest corner reflector ever seen by man. Anytime you see a vertical and horizontal tail surface, that is a stealth no-no. And you'll see a lot of older US military vehicles have that. The F-15, I have an example coming up later. The F-15 is famous for its 2 vertical tail surfaces, and then of course has its horizontal ones immediately there. Then of course we're still using that vehicle, but we're using the F-15EX. What did Boeing do with that? They tilted these a little bit, and that helped the radar cross-section massively, and it cost almost nothing. So knowing these simple rules, which they did not know when they originally designed these vehicles, is enough to save lives, billions of dollars. It's pretty interesting, but we'll keep moving on back through here. So the next thing I talked about was tapered conductivity. So what's going on here? Again, we get to cheat and we can call this all optics. Everyone's familiar with Snell's law. Who here does not know what Snell's law is? All right, real quick, I'm still gonna discuss it. Snell's law is a physics concept that has to do with fundamental geometric optics. Basically, and everyone's familiar with this if you've just had like a glass of water before, light bends whenever it goes through different media, aka different refractive indices, which is just a material dependent parameter, right? If you go from refractive index 1 to refractive index 2, and they are different, you will have some angle of diffraction that will occur. Refraction. And refraction, not diffraction. Depending, it might be this way, it might go that way, but if they're the same, it just keeps on going straight, like it doesn't change media at all. This happens with radar waves too. The difference here is, for our purposes, the material no longer has a refractive index. It has what's known as a conductivity. Everyone knows what that is. Copper's conductive, rubber is not, right? Everything has a conductivity, and we're gonna abuse that fact to stealth our planes. So, they have markers in here. Yeah, whatever. Discontinuities. Just how light bends when it hits a discontinuity or a difference between 2 media. Yeah.
Got more for you.
Oh,
Sebastian, what was that?
what was that? So, a discontinuity is very simple. Let's call this, we'll call this aluminum, and we'll call this copper. These things have similar yet different conductivities. If I am just a block of copper, a block of aluminum, and I have an electromagnetic wave traveling through here, the second that wave hits this discontinuity, right now it was all just current inside of metal. But the second it hits this material discontinuity, it radiates and acts like an antenna. And that's a huge issue because that happens literally all the time, and it's related to some of that tempest stuff that we'll talk about at the end for any of those interested. But this kind of thing happens all the time. Discontinuities in circuits, PCBs. When you're designing high-frequency antennas, high-frequency circuit boards, your whole purpose is to prevent discontinuities. And a funny thing, just for anyone doing circuits later in life, let's say this is all copper. If I have a copper trace of this width, and then I do this, I need like a thicker one or something, maybe there's a pin here. Guess what? Discontinuity. Because unfortunately, conductivity, while it is a material-dependent parameter, actually can change based on just dimensions alone. So this right here, for stealth purposes, is bad because it's going to radiate. And from a designer's purpose, for a circuit board or something, it's also going to radiate and you're going to have problems. So we need to prevent these re-radiations, although it's not possible to prevent them entirely. So we have to mitigate them somehow. And the way we mitigate them in real life is with what's called stealth tape. Literal rolls of tape that they have. Classified tape, it's stupid, it's insane. But they use rolls of tape, and we'll look at some close-up pictures of some vehicles later on, and I'll actually point out where the stealth tape is. A lot of you may have thought that was paint, but it is not paint, it is tape. So, this is just another explanation of what I just drew out. If we go directly from some metal, aircraft wing, front of my wing gets hit by radar, that energy is going to go into the metal and it's going to become just a current inside the metal. It's going to flow through the metal, then it's going to hit the trailing edge of that wing. Now it's no longer metal, it's hitting the air again. If I just go from straight metal right to air, I have a huge re-radiation. It's called sparkling. That's the proper term from a stealth designer's perspective. But if instead of going from gray right to white, we go from gray to light gray to lighter gray to lighter gray to lightest gray to white, we have tiny re-radiations. We lose small amounts of energy as we go, not enough to give a return, but enough to mitigate the large return when we get here. So instead of dumping all our energy at once with one change, we dump our energy incrementally as we go. And that's how the stealth tape is designed. It is rolls of fixed length, and their purpose, as long as you keep it in these fixed length sections, from here to here, it's high to low conductivity as it goes, or low to high. Engines. This is one of the most important things. This is horrible. There's a lot of reasons this is bad. This acts, one, is just a bunch of little mirrors of metal flinging the energy back. It can act as a, it's an oscillation chamber where the energy bounces back and forth and can get magnified sometimes. There's a lot of issues here. Engines are a huge problem, and from a radar return perspective, they're a broadband and a wide lobe issue. Whereas if you just had a flat surface and a wave comes in, if you got lucky and it came in at an angle, it would deflect away, and you'd be fine. Engines, because of all that spinning and complication, it just produces a field, an FOV beam, that makes it really easy to detect you. So, fun fact, from a radar discrimination perspective, we rely a whole bunch on engine returns, not just to help us identify the vehicle, but some of the ways we do it are cool. Is anyone here familiar with the Doppler effect? Ambulance comes towards you, it's compressed, so it goes higher pitch. As it goes away, it is extended, comes lower pitch. Same deal with radar. If you get hit by radar and you're moving faster, that radar frequency compresses, and that's how they tell what your speed is, or one of the ways they can tell what your speed is. You can identify a plane, make and model, just by the Doppler return off of its engine props. There's some crazy stuff you can do. And at the highest level, the stuff you can do is like comically top secret, but also very, very cool. But obviously we can't allow this to stand. So we've had things in the past, and they were shit. This vehicle is historic and is amazing, and it did its job great. The second it dropped its 2 GPS-guided bombs, it was a sitting duck. Garbage. But it still was awesome. How did this guy mitigate its engine inlets? Well, we can see its engine inlets right here. Well, they're front-facing, just like the problem that we just mentioned. But how they did it was they put a grid. Anyone know what a Faraday cage is? They built a Faraday cage around their engine inlet. They spaced the cage such that it would reflect waves away, and they angled it such that it would reflect it up and away. Problem. Who here knows what happens when you put a cage in front of an engine inlet?
They can't breathe.
They can't breathe. So this thing was stupid and slow because it couldn't breathe. So obviously we can't allow that to continue because, F-22 Raptor, F-35, these things are high-performance aerobatic machines, right? So they need air. So here's an F-35 head-on. You see any props in there? It's a little dark, but you see any props? No. But there's also no cage. So how are they preventing the radar returns? Well, we use what's known as an S-duct, or a serpentine duct. This basically, as I'm sure you can probably assume what this is an F-22, whose inlet is right here. Your air comes in, all you do is add a little bend in the path, out your engine. So what happens is the radar gets stuck inside and can't escape. Also, you coat the inside with radar absorbent material. You do a bunch of stuff like that, but the other thing you do is there's a bunch of stuff here, like waveguide beyond cutoff, total internal reflection, all that. It helps. It lets you mitigate your returns. And this is how we keep our vehicles, one, from being identified really easily while they're flying around, and two, from just blasting out radar returns like nobody's business. Next one. You want to avoid long, straight edges where you can. It's obviously not always avoidable. Look at this. That's one long and straight edge if I've ever seen one. But there are places where it can be avoided. Every single access hatch on the F-35 has serrated edges. You can see it everywhere. Looks like hexagons. The point of serrated edges is to prevent flat traveling paths by creating sharp points. The longer a flat path is, the easier it is for radar to reflect off of it. But the shorter it is, the harder it gets. So what you do is you break up these long straight paths by adding little serrations everywhere. And then of course the B2, look at the engine inlet. Serrations. Anywhere that there would have been a flat path, you make a bunch of short paths. And even better, those short paths happen to be at 45-degree angles to one another. That's the golden rule, that's what we like. We hate 90-degree angles. And of course, next, we have canopies. Obviously, you need to be able to see through this. And because of that, you can't just coat it in RAM, because RAM is not see-through. You can't just, hope. Well, sometimes we do just do the whole put a camera on the outside and hope. But in real life, what we do is we coat them with certain materials. This is an F-22 Raptor canopy. Everyone knows that famous golden hue. This is a coating of what's called indium tin oxide. That's the most common coating. The F-35, while it's not golden, also uses a coating of indium tin oxide. And basically, this is not radar absorbent. This is totally reflective. Just bounces it off. Because the instruments inside are way worse than the return that a canopy can give. So they'd rather give you a free return off a canopy than give you a return off of all of these square instruments inside of the cockpit. And this goes for basically every vehicle, including commercial airliners. They also do have indium tin oxide, but theirs is for anti-frost purposes. This coating's a lot thicker. We no longer have the restriction of just using aluminum or other metals for our airframes. We have technology advanced enough to get away with using strong composites, and they give us a lot of benefits. They're lighter weight, they're better temperature tolerance, all that kind of stuff. But another benefit they give us, in certain instances, is that they're what's known as radar penetrable, also known as the electromagnetic waves just transmit through them. Like that whole impossible case I mentioned earlier. Ideally, you just want to be invisible and it just passes on through. Well, the answer is we actually can do that to a certain extent, and we do. However, we can't do it for everything. Metal is still important, and where there's metal, there are radar returns. So we have no choice but to have the other mitigations in place, because we can't just skate by with a composite plane. But we can skate by a lot. You'll see a lot of wing portions, if you look at a F-22 from the top or other vehicles, often they'll cheat and they'll have like large portions of their chassis or their wings will have some type of composite plate which allows the radar to just go through. So they have a better chance of not getting detected if they get hit from the top or the bottom, that kind of stuff. So those are all the entry-level ideas of what you want to look for and what you can use to improve the radar cross-section and stealth properties of a vehicle from a radar perspective. It's a whole other ballgame when you start talking optics. But we're going to start with some quizzes here. Based on what we've said thus far, who has a better radar cross-section? These vehicles are about the exact same size. We have an F-15, we have an F-22. Who wants to go first?
I'm pretty sure the F-22 has the larger RCS. I would believe it's the F-15.
You think the F-15 is the larger RCS?
Yes.
You are correct. But why?
Well, because it makes use of 90-degree angles, which makes it easier to detect.
That's a big problem.
Right there. Those big weights.
Bunch of 90-degree angles. This picture's a little hard to see, but what's another issue?
Less serrations compared to the F-22.
Less serrations. They did not know about edge lengthening or edge shortening. Any other issues? F-15?
A lot of external pieces that aren't built into the frame.
Okay. No internal weapons bays. All that stuff's on the outside.
Back coating on the cockpit window. I don't see it on there unless it's clear.
Yes, they did not yet use reflective coatings.
Engine inlets.
Engines are straight on. So this thing sucked. From a radar perspective, excellent vehicle. But That's why we replaced it with the F-15EX, all that kind of stuff. So there's a whole bunch of stuff here, and it's good to see, right? What we're getting out of this, we've got V-tails, we've got serpentine ducting, we've got coatings, all that. And then also, again, both of them do make use of the swept wing. He did it unintentionally, he did it intentionally, right? Just so happened to be good from an aerospace perspective as well. Another quiz, who has a larger RCS? Crying Baby or B-21?
Crying baby.
Crying Baby does have a larger RCS than the B-21. As we said, the radar cross-section of a human, at least an adult human, probably smaller for the baby, is approximately a meter. Let's call it half a meter for the baby. The B-21, of course, is supposed to be better than the B-2. Therefore, it has a radar cross-section less than a Bumblebee, if not better. This one's harder. Who has a larger RCS? F-16 or the Russian S-70?
I wanna say the S-70 because the F-16 has a large angle, but I also, it has a, what looks like from this angle to be a 90-degree angle, but I also see it has the coating there, so maybe I'm wrong.
What do you got?
F-16, it's got too many weapons on the outside that give it away.
On the outside.
Anything else? Anyone else? So this is a bit, what do you got?
Well, I mean, the S-70, it looks like it has the sprayed-on engine. Maybe, I could be seeing that wrong.
What'd you say sprayed on?
The engine, you can see the turbine, maybe, I'm not sure.
So, what I'll say, we'll do a quick thing real quick. So obviously the S-70 looks a lot like the Dorito, the B-2. And another thing I mentioned, I forgot to mention, a lot of vehicles, a really good way, so you're a plane, right, you're in the air, to mitigate the whole engine problem, put your inlets just on the top. They hit you from the bottom, no inlets at all, right? And as we see in this picture, the old S-70 does have an inlet on top. But, and the F-16, bunch of drop tanks, weapon mounts, that's a 90-degree or a correct 90-degree angle, just not amazing. But the answer here is the F-16 is better. And the reason is the F-16 makes use of RAM coatings, American RAM coatings. We had American designers on all the trailing edges. We use stealth tape. We use all these tricks alongside active electronic countermeasure methods. The Russians, this is a very good lesson in what something looks like versus how it's built. And some of you may have seen the news last month or two of the 2 Chinese stealth fighters that came out, right? The J-36 and then the other one, the tiny one, yeah. And everyone lost their minds. They're like, oh my God, America's gonna lose. The Chinese have 6th generation stealth fighters. They don't even have tails. Look at them, no tails. They're invisible. Well, the answer is they're crap. Because shaping alone is what we like to look for. We like visual things, right? And I just went on this whole rant, this whole slide deck about shaping, but then there's also those other soft things. RAM, edge coating, assembly. If we were to zoom in real close on this picture, there's rivets.
Yeah.
Metal rivets sticking off the wing.
And screws too.
And screws.
Those would be reflective.
And metal plates. They have very little mitigation. This thing got shot down by Ukrainian air defense. That's how you know you lost. So,
It was a Patriot, wasn't it?
huh?
It was a Patriot, wasn't it?
I mean, it was ours, but it's 40 years old, so it's fun. But so in this case, this was a trick question. I knew everyone would go for the F-16 because this looks like the stealth Dorito. But unfortunately, it's not always just the shaping. There's a lot that comes into play. And at the end of the day, radar absorbent material, as I mentioned earlier, does a lot of legwork, but only really starts to break down against really, really advanced radars. But the only people who have those really, really advanced radars are us, our allies, and a little bit of China. So from a tactical perspective, this thing's not great compared to this vehicle, which while it does have its problems, we did fix it. And a good thing to note is a lot of the vertical surfaces, we can and have replaced them with the whole penetrable composite stuff. So they stop reflecting.
So in Top Gun, they fly in F-14 with the wings go in and out. Did that have to do anything with radar detection or anything?
That had to do with Navy requirements regarding being able to cruise and be energy efficient, as in winged out. And then when you needed to go faster and faster and go supersonic, you fold your wings in.
So it didn't affect radar in any way then?
I mean, it would affect radar cross section, but it wasn't designed for radar cross section.
Okay.
It was designed for aeronautics, so.
Was it sort of the similar reason to why the F-15 beat out the MiGs, the Soviet MiGs? Did radar play in any way part of it for the F-15 beating the MiGs?
Americans built up radar guided, so missiles are guided by radar nowadays. There are things like, infrared and EOIR systems, like the AIM, Sidewinder, all that kind of stuff. But most missile systems are radar guided. If your radar cross section is high, our missiles hit you. That's the whole point. That's what you gotta avoid. But yes. You may not like it, but this is what peak performance looks like. So, this is a bit of a joke, but this is real. This vehicle, funny enough, had a smaller radar cross-section than the F-117. This is the tacit blue demonstrator for Northrop Grumman back in the day. And they hated it because it's ugly, but it had an excellent radar cross-section. And it's got some of the tricks. Now, to be fair, this thing's almost entirely built up of that composite material, so it's penetrable, so it doesn't reflect a lot. V-tails, again, no vertical, but you're allowed to do this, that's fair play. Then engine inlet on top. It was decent. And another thing, if you have really, really sharp edges, that's actually fairly good. That helps a lot. All right. In conclusion, we've discussed a lot of things. The concept of stealth, what is a radar cross-section, little intro as to what the aspect angle is. And keep the aspect angle in your mind. A lot of people don't really understand that. But nowadays, you'll start seeing the buzzword all aspect stealth coming around. And particularly as the FAXX, the Navy one, and the F-47, the NGAD, start ramping up in development, we start seeing more and more of this, 6th-gen push in the news. You're gonna start seeing a whole bunch of all aspect stealth, this and that. And it's important to note what that means. A lot of people are gonna see this and be like, oh, what does that mean? But really all it means is, from any viewing angle, radar-wise, you basically maintain a very high level of stealth, or a low radar cross-section. We discussed optimal approximations and how it can help you as a designer of a vehicle. Because again, these things are not designed by individuals, they are designed by groups, teams, and in most cases, almost governments, levels of people. You're talking about, 500, 1,000 people working together to build something like this and make it right. And with regard to most vehicles, RAM and these stealth coatings are not permanent. They have to be maintained. They are the majority of the cost of the US Air Force is maintaining RAM almost always, at least for vehicle maintenance wise. You have to paint this stuff on, you gotta apply the tape, and it takes large teams of skilled servicemen to do that. And we have to do it all the time. We have temperature controlled hangars for B-2s because we have to maintain the stability of their stealth coatings. Right? Additionally, how to stealth a plane. What are the main things to look for? If I gave you a plane right now and said, I need you to drop this thing's radar cross-section, I put a 737 in front of you and say, you've got 20 days and 200 million, make this thing stealth. You'd be better than most. It would still fail, unfortunately, but it would be a good try. It'd be a better try than the average person. And then, of course, we discussed corner reflectors, discontinuities, engine inlets, edge shaping, the works. Fuck. Any questions? General questions. It could be about anything. I've done a lot. Stealth is something I do like, but I can really talk anything. But while that's happening, we'll do this first. So while this is all going, everyone feel free to do that. And if anyone does need to sign in, I can bring that back up for you. So.
Oh, I need to sign in.
Okay, all right, we'll let this happen and then I'll bring it back. Any questions?
You mentioned you were going to show a picture of how the tape. Basically, you were showing.
Yeah, I'll go back to the zoomed in F-35 in a second. Everyone good on that? Yeah, what's up?
What would be the stealthiest vehicle that the U.S. has right now?
Technically, again, it's all the actual answer is classified and I don't know it. But officially, it's probably technically the F-22. I believe it is better than the B-2. But I think the B-21 The new B2, which isn't technically fielded yet, probably beats out the F-22. And the last presentation I gave about a month ago was on electronic warfare stuff, and I've mentioned in here a couple times about ECM, electronic countermeasure techniques. Most modern stealth, like all the stuff I've mentioned, is extremely important. If you don't have this, you're screwed. But modern radar beats most of this still. So the answer is there's a whole other set of solutions necessary in tandem with all of this, and it's electronic warfare techniques. Jamming, decoys, suppression systems, all that stuff comes bog standard with every single one of these vehicles. And that's what really pushes us the extra mile and allows the United States to have and maintain air dominance. But if you were to be asked that question on an exam, I'd say F-22 or B-21. Everyone good on that? All right, we'll go back to the front real quick. For the sign-in. If anyone need to do that, what's up?
What do you think the number one compromise that the United States is making right now on their stealth design is?
Speed. That's the whole push for better RAM. We've advanced so much in terms of engines, speed. We're pushing things that could be hypersonic nowadays. And we're almost to the whole mixed phase engine where you've got a turbofan and then you get fast enough, you transition to a scramjet or a ramjet system. Speed is ultimately like the ultimate decider. And our RAM limits us drastically. And we can't really bypass that. We need it. So a lot of our efforts have gone towards improving RAM's temperature stability, and we're getting there. There's a lot of work. Lockheed Martin in 2008 patented a broadband stealth composite made of nanotubes, carbon nanotubes, and it goes from like 10 kilohertz to 80 gigahertz, and it was like keyed in specifically for like Russian stuff. But that kind of thinking, like we need to get away from the whole I spray on the coding every mission, because that's a huge issue, and it costs money, manpower, time, and worst of all, it's not as good as it could be, and it just straight up limits you. Like I'm sure that an F-22 can go way faster, but it's limited by its coding alone. Like it can't, otherwise it's gonna start showing up. Yeah, it's ridiculous. But real quick, we're gonna drop back to the F-35 to talk the paint. Where is it? There it is. It's hard to see on here, but whenever you see this light gray on the F-35, that's the tape. And you'll often see it around a lot of the access hatch edges. Let me go find a picture on Google real quick of the, what is this one? How did it sign me in? Bruh. 1 second, it doesn't like me. Bruh.
Just showing that.
Am I? Oh, caps lock is on.
He was just like this at work, dude.
Yay. Alright. But it is F-35. It's called
It's the Lightning II.
the ladder.
Well, wait, the ladder.
Yeah, I'm looking for the ladder. So this thing, it looks so stupid, but it's a good system. The way that they get in, trying to find a good picture. Can I like full screen this? Ew, Reddit. All right, this image is a good way. So this access hatch again, good example of the whole make things short. This could have been a rectangular hatch, but they made it into this weird hexagon shape solely to do the whole let's mitigate long edges. This light gray around the edge, that's all the stuff tape. Whenever you see that, they're taping it on around those edges. And they do spend a lot of time on edges because the waves, as mentioned, travel along these edges. That's why, one, they break them so they don't get to travel the whole way and radiate at a higher power. But they also do the whole tapered conductivity, so as they travel, they get weaker, as opposed to getting stronger, which is not great. But a whole other thing that I did forget to mention here, kind of left it out just from a complication standpoint, no, we're not making new slides, is everyone knows that, radars and radio waves have frequencies, right? You could be in the kilohertz, you could be in the megahertz, gigahertz, the works. Unfortunately, depending on what the frequency of your radar is, completely changes your stealth properties. There are very, very few powers that have access to the technology to have what's called wideband radar absorbent material or radar, stealth solutions. We've got us, United States, and a couple other countries are close. It's expensive and it's hard. It's really easy to do narrowband solutions. So if you have a really good intelligence network who knows exactly what radar frequency someone's using, you can very cheaply design absorbers. In fact, they're so easy you can make them out of literal copper tape. You just make funny shapes. It kind of looks like magic, honestly, like writing sigils and stuff. But it's cool. But it's not great because it's one frequency, and hopefully everyone's aware, modern radars do not use one frequency. We use spread spectrum coherent systems. They hop frequencies, they radiate energy across multiple frequencies. It's super hard to do this nowadays, so you basically have no choice but to go for wideband solutions, which is expensive and complicated, but it's worth it because the alternative is getting shot down. Anything else?
Why is it so normal for them to put out their designs for the world to see? Because you talked about how if they have dark paint and tape and stuff, it can increase the heat, and that can be tracked using thermal signatures. So why would they tell everyone what their plans are?
What I'll say is, historically they didn't. They kept the planes really, really hidden. But now everyone has a camera, including the servicemen who fly on these, who may be a little younger and dumber than expected sometimes. So unfortunately, the answer is they keep it as secret as they can. They didn't willingly go out and say, oh yeah, we've got stealth tape, but I can totally tell you some avionics technician got drunk somewhere and said it to someone they shouldn't. But the answer is we do our best to keep our secrets, but luckily, often you don't need to keep the fact that something exists secret to be secure, you just need to keep exact information secret. At least from a government perspective, if you have a clearance, that's really they don't care about most things, but if it's dates, numbers, that's what they're gonna be okay, well, you can keep that secret. If you have just a little bit of obfuscation, it's enough. But the whole heating thing, what I'll say is one of the benefits is most of the time, our vehicles are not moving so fast that they're heating themselves up. That's only if you're doing very high intensity aerobatic stuff beyond Mach 1. Most of the time we're not doing that. In that case, as we move, we cool ourselves down. It only starts becoming a problem when you start getting too fast, and now you're heating up from absorbing radar and you're heating up from just moving through the air. So it's a rare problem. But laser weapons are becoming better, but they're not quite good enough to take down full-on planes yet. It's more of an anti-drone thing and an anti-small munition missile type thing.
2 questions. One, you mentioned you had a bunch of these lectures up on YouTube. Do you know what channel that is?
Yes, let me pull that up. It is YouTube HKN, no, sorry, UAH HKN Tech Talks. Bonk. This is the channel right here. There are 4 lectures up. There's about to be the last lecture, automatic target recognition, is going to go up this evening along with this lecture. So they'll be up. The ones we have so far is the original stealth technology talk. Watch this at your own peril. This is where I did all the math. This one hurts.
Oh, yeah.
Sean Mitchell, he's an engineer at Cummins Aerospace, great guy. He did Introduction to Guidance, Navigation, and Control. And in a lot of Sean's stuff, he has GitHub repos that have demonstrators that allow you to do stuff. So for this, he built this thing where you can actually test out your own guidance algorithm. So you can tweak the values and see how it completely changes how your system is able to traverse points in space. So this one is awesome. A quick note about that one, the CEO of his company showed up unannounced to that one, so that was funny. I had to clean up the room fast. Then we've got another one from Sean, Introduction to Vision-Based / Machine Learning Navigation Technique. So this is how to move yourself, your vehicle, your robot through space, only via using cameras. How do you tell where you are and where you're going with images alone? Sounds super advanced, and it is, but we have been doing it with Tomahawk missiles forever. And then the last one I did is Introduction to Electronic Warfare. So this is the one where I discuss, there is also some math in there, unfortunately, but it discusses a lot of really the cutting edge of what we do with regards to electronic warfare. That is the primary way we do the whole to not get shot down thing. And even cooler, we can do stuff nowadays. I've been talking a lot about this radar cross-section thing. We have technology that lets us simulate and create fake radar cross-sections of known vehicles. We just have a library of these things. And we have a bunch of vehicles that can do it. The F-35 also can, but my favorite one, it's the ADBM Mauled Cruise Missile. It has no explosive in it. It just has an electronic warfare package, and its sole purpose is to fly around the battlefield and just be a fake plane. The enemy radars see this tiny, cheap little cruise missile. They're like, oh my God, it's a B-2 Spirit, throw everything we've got at it, and they hit nothing. So it's really cool. Most people did not know about those things until they started popping up in Ukraine. We gave a bunch of them to the Ukrainians.
That's what they did with that first offensive. They used that as paired with Storm Shadows. The Storm Shadows came behind them.
Yeah, when you have the ability to completely waste the time of your opponent, you can basically do as you please, because you're just going to make your fake radar cross-section the scariest, most damaging possible vehicle, and they're going to waste all their time going after that, and then you can just send a bunch of your stuff in from behind and just destroy everything. Super simple. But yeah, that's the website. You had another question?
Yeah, so a bunch of late Cold War planes, you'll see like the nose section is completely circular, and intuitively that would be a good idea because it's scattering everything in every direction. But then newer stuff, you'll see it kind of has like an angle, which intuitively you could say is a bad idea. What's the reason for that?
The answer is the circle is actually a terrible idea.
Okay.
And it comes down, where did I put the marker? Oh, it's over here. It comes down to wavelength. So a circle normally is fine, right? So if we have a radar wave coming in, let's just treat it like it's a ray, bounces, and then if it's perfect, it bounces right back. Because a perfect planar point is just ping. But in reality, again, this is not a laser, it's a wave front. So you get a bunch of scatters. But remember the whole long straight thing the waves can travel? What happens most of the time, if you have a smooth surface or reflector like this, you get this. It travels, hits too sharp of a discontinuity here, and just reflects right back to you. And this is actually a function of the wavelength. So if this diameter, I think it's like 1/10 or less of the wavelength of the radar wave, this will happen. So they put that discontinuity there, and then put the tape. To force it to lose energy so it doesn't just come flying back. Because this is a bad one, because if we're looking at this, that means I'm getting hit from the side, because my nose comes this way. That's a bad one, because you're getting hit from the side's already a pretty bad case scenario. You want to always be face on, normally. Anything else?
With the composite symbol transparency, where does that carbon fiber fit into that? Because no carbon fiber is transparent, and like where do the carbon nanotubes that fit into that? Does it act like carbon fiber, or is it different?
I mean, fundamentally, carbon's carbon. Like the fiber and the tubing and the buckyballs, we do that shaping, but from a electronics and material parameter perspective, they are the same thing. Except for they can do some cheating with the carbon nanotubes, where carbon fiber is like a planar laminated material where you've got sheets of carbon interspersed by polymers and adhesives. The carbon fiber like nanotube stuff that they do, it's still carbon, but it's graphene. So it has the magic bullshit that graphene gets to take advantage of, the whole 1.3 degree quantum curve crap. So the other answer is the carbon nanotube stuff that they do. It is not laminate. It is randomly dispersed. So all these different angles act like short dipoles. Dipole's like an antenna. Who here knows what chaff is? Okay, a couple people. So radar chaff is a type of countermeasure. Think of it as a flare for radar. When you shoot this stuff out, it comes in these little canisters. It looks like hair. But each of these little strands of hair, think of it as like a metal wire, like a little metal wire. I don't know. And they're varying lengths. And as I just mentioned, the circle, this whole 1/10 wavelength of the radar thing, or of the radar wave thing, can result in certain special interactions. Same goes for chaff. So you have these little fibers of varying lengths. That's the same trick they're doing, where this chaff is designed to reflect. So you would deploy this to shield yourself from getting hit. You're trying to trick the missile into hitting one of these who happens to have a larger cross-section in the moment. If you were to take something that's similar, carbon is highly conductive. So if you take something like carbon nanotubes and you put it in a bunch of random angles, random sizes inside of a polymer, you can key in something that absorbs really, really well. And that's how they do that RAM stuff. It's one of the ways. The patent is public. You can just go read it. It doesn't have everything. obviously.
Yeah.
But it has enough. But from a RAM design perspective, I believe it's this book. This book right here, Radar Cross-Section Analysis and Control, has entire chapters on designing RAM. Let me make sure. Yeah, starting at section 4.5 with the absorber coatings, it's got your theorems, your analytical techniques, your designs of absorbers. There's a whole bunch that goes on there. Also, everyone UH student, most people, makes sense. You all get, as a student, free access to IEEE Explore through the Sandon Library. You can log into IEEE Explore and straight up just type like radar cross-section or absorber, and you'll see a bunch of cutting-edge papers of people in universities just making stealth coatings for fairly cheap. So it's a good way to learn, because those papers are free and open access to you guys right now. But yeah, a bunch of fun stuff. But view slideshow. All right, so your hooks. How do you learn more? Well, the first answer is become an electrical engineer. I'm sure that might not be, ideal for most people, but truly, radar, stealth coding, all this stuff, you just have to be an RF freak to know what's going on at the end of the day. Radio frequency is black magic. It will never stop being black magic. And you gotta kind of do your best to learn what's going on, and you do that by taking EMAG and radar and RF courses. So a good one, Dr. Poor teaches the first two. Dr. Maria Poor, she teaches EE308, which is electromagnetic engineering, your standard E&M course. She teaches antenna design and analysis at the undergraduate and graduate level. We've got Dr. Lawrence, who teaches the radar systems courses, and there's more. There's higher level radar courses here at UAH. I highly recommend this text. The unfortunate thing about these books is that they're prohibitively expensive, but they're great resources. And what I can assure you is if you Google this title, a free PDF will be one of the first sources on Google. So if you do really want to read it, you can just steal it. Right? I'm not making money off it, I don't care. But this book's great. Radar cross-section engineering, radar and laser cross-section engineering. The best part is at the end of this, it gets into optical suppression of your signatures, which is super important because that's becoming the preferred option. And then we've got several other texts, but what I'll say, a very specific thing here, most of the stuff I talk about is defense related because it's what I do, I like to talk about it. There's a lot of stuff that's super, super important. And there's things that have dual use technologies, nuclear energy, right? You can either power a city or blow up a city, right? Same deal. There's a lot of stuff that's really, really classified, unfortunately, even though it's really cool and it's hard to get into. And a part of that is if you just Google stuff, you will find nonsense. So really, the only way to really, really get good without just having a job in it, which is hard to get in the first place, you have no choice but to buy the books. Because the books are government approved. Every single one of these books, let me open the radar laser one. Pretty sure they write right at the front. Where is it? Yeah. Copyright 2019 by the American Institute of Aeronautics and Astronautics. That's a club on campus. You can join AIAA if you like, highly recommend it. So that's a private org who just does AIAA stuff. The US government has a worldwide royalty-free license to exercise all rights under copyright claimed herein for governmental purposes. All other rights, so they just own it, right? These people wrote it, this author is not the government, he's a private citizen, and yet he signed away every single right to this book. Because anything that touches a little too close, the government gets a say because ITAR exists. So you have no choice but to follow the International Trade and Arms Regulations Act, right? So all of these books have that same rule, but because it is government approved, it's hopefully not misinformation, or at least it's as close to non-misinformation as you'll get with regards to tactically viable technology, which is cool. The rest of the books, so first one as mentioned by David C. Jen, Radar and Laser Cross-Section. Another one, Active. So this is that whole, what I mentioned, electronic warfare stuff. Active. Whenever you see active, think I'm actively doing something. All the stuff we've mentioned have been passive techniques, as in it's there, and theoretically you just let it sit and it'll do its job. This is I actively do something. I actively use a radar or my own antennas to trick you, that kind of thing. Excellent text. Next one up is Radar Cross-Section Analysis and Control. This one is really nice. This one's actually not that expensive. I think this one was like $50. Still kind of steep for a book. But again, free PDFs exist. This book is awesome for anyone who thinks planes are cool, just design planes. It only has one single 10-page chapter that has anything to do with stealth design, but it's really helpful from an aerodynamicist perspective. So this one talks a lot about your wing sweep and your cockpit and your serpentine inlet ducts. This one has a lot about that. And then last but not least, the tome. This is the Radar Handbook by Meryl Skolnick. This is the first edition. I have 2 of these. It's up to the 3rd edition now. Do not buy the 3rd edition. It is like $200. If you just Google this, there's a PDF first thing. I've confirmed that. So we're good. We already signed up, so. All right, thanks everyone for coming. Good luck on finals. Best of luck.